The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Good morning, everyone, wherever you are. I'd like to welcome you to this short course entitled Understanding Lasers and Fiber Optics. And before I do anything, I'd like to tell you what sort of topics I'll be covering. I will start with the many reasons why we're all interested in lasers today. Then I would like to talk about the key properties of lasers that make all these applications possible. Then once we understand these key properties, then I would like to discuss how these properties come about. And then we'll go describing the operation of a simple laser and even show you a demonstration how a simple laser works, what you need to make things happen. And then we'll look at a variety of properties of this simple laser. Then we go look at other issues and problems to do with lasers. Lasers are not perfect, and if you don't treat them right, they can give you some problems. And in some cases, you can get rid of these problems. In some cases, well, you try to minimize them. Then I will discuss the variety of lasers and what makes them tick, because we have all kinds of lasers today, and it's nice to get a feel for the variety of them and how they work, how they get pumped, and so on. Then I'm going to change topics, and I will switch to the basics of fiber optics and to familiarize you with what's going on in fiber optics, what are the issues, and but mainly the emphasis on basics. And then finally, I'll have a few words to say about future developments in lasers and fiber optics. Now, how will I present the material? Well, I will be using a very simplified treatment, and the reason is so that people without specialized background can follow. I will emphasize only fundamentals and not the details, so that the understanding can be made very easy. And I will use very little math. I will certainly not emphasize mathematics, because I would like to make it very understandable, and I don't want to switch people off. And most important, I'll be using lots of demonstrations to illustrate some of the fundamental phenomena in lasers and also in fiber optics. So now I think we're ready to start the course, and the first topic that I had is, why is there so much interest in lasers? Well, the reason why there's so much interest is because lasers have these unique properties that we're going to discuss. And it's these unique properties that make all these applications happen. Now, these properties have created all sorts of new devices. We'll mention a few of them briefly. And also have improved many existing devices. So the laser has been very nice in lots of fields. Just to give you some example of just a few applications. Well, let's just look at them just briefly. The barcode readers. Everybody's familiar today with barcode readers. Now, lasers certainly make that possible. And of course, the compact discs, computer printers, laser color copiers, all these depend on some of these properties of lasers that we'll be discussing. Then, of course, you've seen the laser shows, and that certainly uses a specific laser property. Then there is holography. That's the 3D imaging, the hologram that you see on credit cards, that's all due to lasers. Then lasers are also used for precise control of position and motion. For example, sensors. Lasers today can measure all kinds of things with fiber optics, without fiber optics, or what have you. The big area of today and the future is fiber optic communication. And again, it involves not only fiber optics, but also lasers. So we'll see how the properties of lasers are used for fiber optic communication. Then we have topics like materials processing, like cutting, drilling, welding, and so on in materials. There is a whole slew of techniques for non-destructive testing. This is the testing of systems without having to destroy them. And lasers are quite sensitive, and they can do that without the need to damage the systems. Then we go to spectroscopy, and a variety of spectroscopic techniques have been opened up by the laser. Chemical processing. Then we get to the military application, military systems. And we hear a lot about the use of lasers in the military. And finally, last but not least, we have medical procedures, medical diagnostics using lasers. And all these applications come about because of very few unique properties of lasers. And certainly in this course, we want to make sure that we understand those and how they come about. In fact, we find lasers all over the place today. We find them in the home, in the factory, in hospitals, in laboratory, in the military, wherever it is, even in space, in the ocean, and even in the theater. So you can see lasers are playing a very important role in our lives today. All right, so now I would like to go to the next topic, and that is the unique properties of lasers. All right, so what are these unique properties? Well, let's start with property number one. Now, some people refer to it as high monochromaticity. What is monochromaticity? Well, that means it's one color. And we'll have to see what people mean by that. Others refer to it as a source of light that has very narrow spectral width. Again, we want to see what it means. And others may refer to this property as something that has a high temporal coherence. And we want to understand what the meaning of all these things are. So let's start first with the narrow spectral width, or the single color. Here what I have, and I hope you can see it, the colors of the spectrum. I did the coloring myself, and it's pretty close to the spectrum with whatever colors I had. Now, the visible range, as we all know, extends from about 4,500 angstroms to about 6,500 angstroms in the red, which is about, 2,000 angstroms or so. And that's the visible, essentially that's the visible range. Now, when we compare light sources to this range, for example, the spectral lamp that has a very narrow line width, or spectral width, here it is. Here's the typical output of a spectral lamp, let's say here in the yellow, and the width over which there's radiation could be as low as 1/10 of an angstrom, okay, or 0.1 angstroms, or in terms of frequency, it's 10 gigahertz. And then you can get some lamps that have smaller line widths, or you can even get them with broader line widths depending on the conditions of the discharge and so on. Now, when we come to lasers, the line width is extremely narrow. The spectral width is extremely narrow. And it can be in the megahertz, but can also be in the microhertz. Now remember, this is 10 to the minus 6 hertz, or even smaller. So the laser is an incredible kind of device when it comes to the spectral width. The line width can be extremely narrow. Now, I know in practice that's not what one measures, but if you get rid of some of the effects we'll talk about, external effects, then you should be able to see line widths as narrow as that. All right? So the laser then is extremely narrow. Let's see how you might measure the spectral width. So you don't have to take my word for it. Let's see how you might measure it. Well, if you took a typical spectral lamp here, and then collect some of the light from it and put it into a spectrometer or some other device that measures the spectrum, then what you get a plot like this, intensity versus wavelength. And here you can either plot wavelength or you can plot frequency, depending on the kind of work you do. And then you'll see some blob like this, and it has a certain width over which the source radiates. And we call it either delta lambda for the width or delta f. Now, when we compare it with a laser, again, we'll do the same thing. We'll take the laser and feed it into a spectrometer or some other device. The width here can be very narrow, and just like I said before, can be even as narrow as microhertz. But these are only under special conditions. But even if it's megahertz or tens of megahertz, it's way narrower than you get from a lamp. So again, if you're not sure, then you have to do the experiment and check indeed that the laser does give you an extremely narrow line width. All right, so that's basically then the line width of the laser. Now the next thing is, what about high temporal coherence? What has that got to do with the line width of the laser? All right, so now we need to explain that topic. Now, let's start first with a wave, with a sine wave. Okay, now this sine wave, let's say, starts from minus infinity in terms of time and goes all the way to plus infinity, completely uninterrupted, a pure sine wave. Now, if you had a wave like this that has a constant frequency and a constant amplitude, then when you look at its spectrum in the frequency domain, what you see something that's, let's say, centered at f0, f sub 0, with a width, delta f here, very close to 0. All right? Now, this is a source of radiation. It's like a sine wave like this that has what we call perfect temporal coherence or time coherence. And that's the best, essentially the best that one can have. Now, in practice, light sources do not radiate for such a long time without any phase interruption. So let's say we have a light source like this that radiates only for a time tau and then shuts off, for example. Now this one, because it only radiates for a time tau, it's going to have a line width in the frequency domain. It's not going to be a delta function like we had before. And this width, if you do the calculation, this width in terms of frequency is proportional to 1 over the length of this wave train, tau. Again, I put approximate so that I don't get into trouble about the exact numbers, but it's very close to delta f is 1 over tau. So that if tau is very long, then delta f is small, as we've shown you before. But if tau is short, then the line width here will grow. Now, atoms, for example, because this is where we get our radiation from atoms, they radiate in bursts like this. Now, if they radiate in bursts like this, then tau sometimes can be quite short, which means that the width of the radiation will be broader. So the shorter this is, then the broader this width. And here I show bursts from other atoms, and when you put them all together, essentially that's what you get. You get a certain width that's characteristic of the time of the uninterrupted radiation of atom. And here we get an interruption, therefore the tau then is only when the wave is uninterrupted. Now, some other atoms will radiate in decaying sinusoids, exponentially decaying sinusoids. It doesn't matter. The calculation is a little bit trickier, but again, you get a sort of width. And for the purpose of this course, all I'm after is the dominant width, and I'm not worried about little sidebands down here, just the width. And again, you can say that the width here is of the order of 1 over tau, whether it's exponentially decaying or it's looks like this or what have you. All right. Then to summarize now, high temporal coherence means that the radiation time of the atoms without phase interruption is very long, because the line width is 1 over tau, would be very small. And when you have something that has a high temporal coherence, which means tau very long, it means that you can predict the amplitude and the phase of the wave at any time. Because it's a pure wave. In fact, if I go back to this plot over here, so this is where you have infinite coherence. It means that if I know the amplitude and phase of the wave at this time, I can, only with using a clock, I can predict exactly what the amplitude and phase of the wave would be at some other time later. And the separation in the time can be very long. When we get to into sources that radiate like this, then obviously within this time I can predict the amplitude and phase of the wave. But if I stretch the time a little further, bigger than this tau, then I cannot predict anymore the amplitude and the phase, because this is like another waveform that is completely uncorrelated with the first one. So what we call the coherence time now is going to be limited only to this time during which the wave is uninterrupted. Then you might ask, well, what are typical applications of this unique property? Well, the fact that it has narrow line width can be used in communication. Certainly, that's a key property here. In spectroscopy, especially in high-resolution spectroscopy, in interferometry, holography, and a variety of sensors. So that's a key property for many applications. Now, what I'd like to do is discuss the second, what I call the second unique property of lasers. Now, here it is. There are many ways of describing it. One way is that the laser has a highly collimated beam. And we've seen that in laser shows and what have you, that the laser has a highly collimated beam. Other people may use better scientific language and would call it diffraction-limited collimation. And we want to know what that means. To some, the fact that the laser has a very small focus spot is this meaning of this property. And others may call it, again, in a better scientific language, it's a diffraction-limited focusing. All right, so whether it's diffraction-limited collimation, diffraction-limited focusing, or even, as others might call it, a laser has high spatial coherence, they all mean essentially the same thing. And let's find out now what we mean by all these words. All right, let's go back and look at a typical light source. Let's say spectral lamp. We have electrodes here, plus and minus. We have an arc here, and then we collect the light from the arc with a lens, and that's placed at the focus of the lens here. This distance here, f, is the focal length of the lens. So now we try to collimate this light source. Well, what sort of collimation do we get? You can see here that this point, this one end of the discharge, you collect these two rays from here, and you create a collimated beam in this direction. The other end of this arc, for example, the other extreme will give you a collimated beam in this direction. And when you put them together, you have this widely diverging beam. Now, you can easily estimate the angle of this beam. In fact, the angle of the divergence of this beam, theta, is given by h, which is half the size of the source here, in this case it's an arc, it could be a discharge lamp or whatever, half the size of the source divided by the focal length of the lens. And so if you don't like, if this angle is too big, then the only thing you can do is either reduce the size of the source or increase the focal length of the lens. Now, let's look at increasing the focal length of the lens. If you increase the focal length of the lens, it means you've got to put it way far from the source. If you do that, you're going to lose a lot of light. So you may get a better collimation, but there's not going to be much light in it. The other thing to work on is H, the size of the source. And clearly, if you make it smaller and smaller, then the collimation will be better and better. And that's how, pre-laser days, that's how one got collimated beams with a lot of light in them, because you try to generate sources that have that very small size. Now let's see what's the best one can do here. Well, the best one can do is called diffraction-limited collimation. And here, if you do the physics of it, if you have a beam that's of diameter d, then the best you can do, this is now a perfect optical beam, light beam, or what have you, beam electromagnetic radiation, of diameter d, I don't care whether it's microwave, optical, UV, or whatever, then the best you can do in terms of divergence angle is lambda divided by d, lambda being the wavelength of the light dividing by d, as simple as that. And I make it approximate here because it's just a small factor here, which I'm not going to worry about in this course. The critical thing, it depends on the ratio of lambda, the wavelength, over d. The shorter the lambda, the better the collimation. The larger d, the better the collimation, or the smaller is the divergence angle. And it doesn't depend on any source size or anything, because this is due to basic physics of electromagnetic radiation. That's what we call the diffraction limited collimation. That's the best you can do. So keep that in mind. Now, let's compare the output of a laser with this diffraction limited beam. Here's a laser source, and with some optics and what have you, I can create a beam that's diameter d, and if I go check its size further down, I indeed see that the angle here, the angle of divergence, is very close to lambda over d, just like the perfect light source that we talked about before. So you can say that laser is indeed diffraction limited, and again, the divergence is just limited by the wavelength divided by d. While in the case of the light source, we had to worry about the size of the source. And then the other important thing here is that all the laser light can be put into that beam. So we don't need to lose any light because we're not collecting enough. So it's another fantastic kind of property. Now, the applications of this property, let's start with the collimation part. The high degree of collimation can be used, of course, for alignment. You can go to large distances without the beam expanding too much. Certainly you see these barcode readers with the lights flashing. If there was too much divergence, you wouldn't be able to scan the bars because the spacing is very small between them. And certainly if you want to do long distance communication, especially in space, radar, and what have you, high degree of collimation is very, very important. Now, the next thing here is, that I mentioned before, is the very small focus spot, or the diffraction limited focusing. Now, where does that come from? And how does it compare with what we can do without lasers? Well, let's go back to basics, back to our arc lamp here, and then we collect the light as we did before. But now, instead of just collimating, let's put another lens and focus it down. And that's normally how we get intense spots, high intensity focus spots, by, again, taking light from a source and refocusing. Now, it turns out that because the source has a certain size, you're not going to be able to create anything here that's going to be brighter than the source. And again, if you don't believe me, you have to go look up basic physics, and it sort of makes sense that it's very difficult, it's impossible to make this brighter than here. So you cannot increase the brightness as dictated by the source. All right, now what about lasers? All right, before we get to lasers, what's the best one can do? Let's go back to our collimated beam of diameter d. That was our perfect ideal beam. Now if we take that and put a lens here with a focal length f and focus it down, it'll focus down to a very small spot. Now this is the smallest spot that you can get, and the spot size is given by our lambda over d, which we remember from before, multiplied by f, the focal length of the lens. Now if f is approximately d, if you can choose f approximately d, then we have a spot size here that's of the order of the wavelength of light. So again, without having to study hard or remember hard, then we have two things. The collimation is just given, the best collimation you can get is lambda over d, and the focus spot size is lambda. And this is then assumes that it's a perfect light source. All right? So that now let's compare with what the laser can do. All right? So now we bring the laser up. So here's our laser, giving us a beam, collimated beam of diameter d. Put a lens here, focus it down, and I go measure the spot size. And it turns out that the spot size, if I'm careful, is very close to the wavelength of the light. So this means that the laser beam is as ideal and as close to perfect as one can get, both in collimation as well as in focusing. While with a light source, it was difficult to get something that is extremely bright. You can make this, of course, the spot size small here by putting apertures. By putting apertures here, you can make this spot size small, but you cannot have a small spot size with very high intensity, like you can here. In this case, you can put all that laser light, and we'll talk about all kinds of outputs very soon. And then you can put all that into this tiny spot. And that's how you can get these huge intensities. Well, you might say, what are the applications of some of these small focus spots with high intensities? Well, there are all kinds of applications. There's compact discs, for example, that rely on a tiny small spot for the resolution. Certainly for laser printers, and again for materials processing, as I say, for cutting and welding and drilling and so on, and also in medical surgery, where the spot size, for cutting and what have you, has to be pretty small. You don't want to make a huge cut, and also because you have to deliver so much intensity, you need the spot size to be small. Okay, especially like, for example, look at the example of retinal surgery, retinal welding, where you try to weld the retina. The spot size is a key issue, because you can almost get any light source to spot weld the retina. The only problem is it spot welds the entire retina. But here, with a tiny beam, tiny focused beam, you can only weld just small areas. Of course, they're damaged areas, and hopefully you can still see with the rest of the retina. So the small spot size is a key thing to a lot of these applications. Now, I mentioned earlier that some people refer to this property of high collimation or small focus spot to high spatial coherence. So let's see what is meant by that. Here is high spatial coherence. And what we mean by that is that the wave is well behaved in space. Now, before we talked about waves that are well behaved with respect to time. Remember, we showed that the wave continues uninterrupted for long periods of time. That's a very well behaved wave in time. Now we're talking about a well behaved wave in space, which means that we can predict its amplitude and phase at any position at a given time, while before it was at the same position at a different time, but here at any position now, any spatial position, as a function of time and also, of course, of space. So let's look at it. Now, an ideal point source of radiation is over here, and then it puts out, these spherical waves that we're probably used to seeing. If the source is very small, then you have perfect spherical waves. If I don't like a diverging beam and I put a lens here, then I can make this into a collimated beam, and this will be perfectly collimated beam. Which means that for what we call high spatial coherence, means that if I know the amplitude and phase of the wave here, in this position in space, I can also predict the amplitude and phase of the wave in another position in space. And that's great. So whether it's a diverging beam or a collimated beam or so on, if you tell me what the amplitude and phase of the wave here, I can tell you what it's going to be over here, because the wavelength is stable and the spatial behavior is stable. Well, if this doesn't mean much to you, let's look at what a light source puts out. And it's back to our spectral lamp here, or an arc lamp. Now, because we have so many atoms in the source here they're radiating, that we get a mess of a waveform that's coming out. So if I know the amplitude and phase over here, it's pretty impossible for me to predict what the amplitude and phase is going to be at a different location in space, and even as a function of time, because I really have no control over these light sources over here. While in the case of the laser, I can get pretty close to perfect prediction anywhere I want in space, but in a non-laser light source, it's very difficult. Now, I can improve things by making the light source very small, as we showed you before. I take lenses and focus them down, put small apertures, and can sort of create a tiny focus spot. The only problem is there's not much light by the time I do that. While the laser, you can put all the laser light into, let's say, collimated beam or diverging beam that has perfect spatial coherence. All right, so these are two very key properties. Now, what I'd like to do is talk about a few more properties. All right, now here is the next one, which is high power. The laser, as we know, lasers have incredible power. All right, so let's see where that comes from. Here's again a picture of a laser and putting out a beam of light. Now, there are two kinds of lasers. There's what we call CW, or continuous wave lasers, and there's also pulse. So if the output is not continuous and it's pulse, we call it pulse lasers. Some of them can be very short, and so on. All right, now let's see what sort of power levels that we can get from lasers. And these numbers, if you're not familiar with them, they're going to really open your eyes out to what's going on. Now, in terms of continuous lasers, well, we're all familiar, I suppose, with the helium neon laser or semiconductor lasers that put out a few milliwatts. All right, some of us work with bigger lasers that put out sort of watts, and not that many people work with kilowatt lasers. Today, you can buy these lasers for all kinds of applications, and you can also generate even megawatts of continuous lasers. That's 10 to the power 6 watts. That's huge continuous power that comes out from these lasers. Now, in terms of pulse lasers, wow, the numbers get really very big. Here we're talking about, in continuous document, 10 to the 6 watts. Here we're talking about anywhere from 10 to the 9 watts, which is a giga or gigawatt, depending where you come from. And then we also can produce pulse lasers with peak pulse power of 10 to the 12 watts, terawatts, and even 10 to the 15 watts. And I don't know if you've heard of this word here, petawatt. And petawatt means 10 to the 15, in this case 10 to the 15 watts. And also recently, we read that some people have produced exawatt peak power, which is 10 to the 18 watts. And these fantastic fantastic power levels. And we'll see how they generated soon and what we can use them for. But for here, I'll just mention just a few applications of these peak powers. Certainly in materials processing, where you want to do welding, cutting, and what have you. For fusion, today, as we know, there's a big fusion program for many years now that's based on lasers, called laser fusion. And the military, of course, would love to use these high-power lasers, whether pulsed or CW. And certainly, a lot of nonlinear optics application are based on the fact that we have a lot of power in these lasers, because it depends on the intensity. Now, the next property that I want to mention is the tuning range of lasers. Lasers, again, are sources of radiation and can have incredible tuning range. Now, let's see over the spectrum of electromagnetic radiation where lasers are, first of all. We have the visible lasers, the ones we see are basically over here. And they may have a certain tuning, let's say, from here to here. And we'll discuss them later. I mean, here, this is just in a pictorial form. I want to show you where the lasers are. And then maybe as we get into the infrared, there may be other lasers, like this one here, some laser here. Let's say over here is in the far, getting close to the far infrared. There's some lasers that have large tuning range. We go from the visible, we can go to the ultraviolet, or even to the vacuum ultraviolet. And today, we've gone all the way to X-rays. So lasers are found all over the spectrum, all over the electromagnetic spectrum, but their tuning range, or their widths, the spectrum, or the spectral width of the lasers, or the tuning range of the lasers can be quite broad. And then we'll discuss them later. But today we have lasers all over the electromagnetic spectrum. Sure, we may have some gaps here and there, but there are techniques of filling these gaps by mixing techniques and so on that will fill these gaps. And today we really have no excuse to say that I don't have a laser at a specific wavelength, because there are all sorts of techniques to create lasers there if there aren't any lasers there already. Now, the applications of wide tuning range could be in the interaction with specific atoms and molecules, where you need to tune the light sources to be able to interact with specific atoms and molecules to reach their resonances and so on. In studying structure of atoms, molecules, solids, and so on, you need a widely tunable source in the area of spectroscopy. And then for propagation, sometimes, if you want to dodge certain molecules in the atmosphere or in the water and so on, you need to tune the laser away from the absorption of these molecules or atoms. And in medical applications, sometimes you need to tune the laser so that it's at the right wavelength for interacting with tissue or what have you. And it's nice to have lasers that are tunable. Now I have one more key property, and that's it. It's going to be just the fifth one, and here it is, that lasers can produce very short pulse width. Now these are incredibly short pulse width, much shorter than any electronic circuit can generate, and here we are. Here's a laser pulse that one can generate, and the pulse width can be, well, this is big, 10 to the minus 9 second, which is called nanosecond. Certainly we can produce these on a routine basis, picosecond, or 10 to the minus 12 seconds. And today we're very close. The record is that we're very close to 10 to the minus 15 seconds, excuse me, which is a femtosecond. That's incredible. Because even 10 to the minus 12 seconds, it's impossible to reach with electronic sources. So already from below 10 to the minus 12, let's say 10 to the minus 11 or so, this is all lasers, because you can't do it electronically. All right? So again, this is fantastic property of lasers. And let's mention at this stage what are some applications of very short pulses. We can certainly use them to study very fast phenomena, where let's say the relaxation time is so fast that normal techniques don't work. They cannot be used to observe them because they're too long. All right, so in order to study fast phenomena, you need very short pulse lasers. Then, of course, the exciting thing about optical computers, if they will ever come about, is to take advantage of these very short pulses, so you can have faster clocks and so on. And for high-resolution radar and imaging, these very short pulses can give you, again, incredible resolution. And so there are lots of applications of these short pulses, and we'll have something to say about them later. Now, I would like to switch to my next topic, which is how these properties come about. And again, we'll start with the first property, which is this monochromaticity, narrow spectral width, and the high temporal coherence, which I hope you still remember from earlier. The question is, where does this property come from? Okay? So the answer is that the laser is an optical oscillator. And so some people might say, well, what's an optical oscillator? I know it comes out like a sine wave, but what's an optical oscillator? Well, what's an optical oscillator is, first, in order to understand an optical oscillator, you have to understand what an oscillator is. So now we're ready to talk about the properties of an oscillator, and we hope then we can extend it to an optical oscillator, and then we can appreciate where that first property of lasers comes from. So here we are. Let's review the basic properties of oscillators. I know a lot of you know about oscillators, but I have to start at some level, so I'm going to start right here. So if we have here a black box that puts out this sinusoidal oscillation, this perfect sinusoidal oscillation, where the length of this wave train, as we've seen before, goes all the way from minus infinity to plus infinity, very long, uninterrupted, constant amplitude, then in the frequency domain, that, as we've done before, that is that delta function centered at some frequency here that depends on the wavelength of this radiation source. All right, so that's what we generally call an oscillator, and especially electrical oscillators. We see them on an oscilloscope. We see this beautiful sine wave on the oscilloscope, and the source of the oscillation. Well, we'll have to see how that comes about in the case of lasers, and the spectral width is extremely narrow, and we see that electrical oscillators all the time, and we don't even think about it. Now I would like to tell you a little bit about how an oscillator is made, and once we understand an oscillator is made, then we can extend it to the optical domain and then be able to explain how a laser works. Okay, so let's review some background here in oscillators. Well, there are all kinds of oscillators. I'm going to start with a pendulum. Here's a simple pendulum, length d, and I let it swing. What does it do when I let it swing? Well, it'll go backwards and forwards, just like this. It'll generate an oscillation here of the pendulum, which will die down. And the frequency of this oscillation is given by 1 over 2 pi, the square root of g, the acceleration of gravity, divided by d, the length of the pendulum. Now, so the longer d is the smaller the frequency of oscillation. But as we can see, this oscillation dies down. And the question, why does it die down? Well, why does it die down? Because there are some losses. And the losses, for example, come in this pivot here, comes pushing air around, and so on. But basically, it will die down because it's difficult to get rid of all these losses. So we don't have that constant oscillation that I showed you before. Now we go to the frequency domain, reminding you what we did before. Because I have a dying oscillation like this, then if the time constant is tau, then the line width is going to be approximately delta f, which is approximately 1 over tau, and that is directly proportional to the losses. The higher the losses, the larger is the line width, and the shorter is the decay time. All right, so that if I improve the losses, if I reduce the losses, then I can get this to narrow down, and I can get this to last longer. Now, if I, as I just mentioned just now, this is in pictorial form. If I reduce the losses, if I'm clever in reducing the friction in this pivot and so on, I can make the wave last longer, and this width gets narrower. But in order to make it constant amplitude, I have to do something else. All right, this is what I have to do. I have to call on this fellow here to push on this pendulum, so that it stops it from dying down. In a way, what this fellow is doing, he's pushing at the right time, it's really overcoming the losses, whether at the pivot here or pushing air around and so on. So instead of having just a dying oscillation like this, what I end up with a constant amplitude. Because of this fellow here is putting energy into this system and compensating for. So as the amplitude here becomes constant, then the line width here delta F starts to shrink and goes close to 0. So in this way, I produce an oscillator. And in this case, of course, it's a pendulum oscillator that's used like a clock and so on. But I do need this energy source, this person here, to overcome the losses. Now, this is not the only type of oscillator. I have all kinds. Let's say I have a mass spring system. I can make that into oscillator. Let's say here I have a spring, and there's a mass connected to it. And then if I pull the mass away, it's going to wobble backwards and forwards. It's going to oscillate. Again, it's going to be a dying oscillation like this because of, well, friction. Mass friction has a friction between the mass and the stable, and losses in the spring, and so on. The frequency here will be determined by the square root of the spring constant k and divided by the mass. If I change the mass, I change the frequency, and so on. And so again, just like in the pendulum, it's a dying oscillation and has in the frequency domain, has a certain width, and the width is proportional to 1 over tau, and that's again proportional to losses. If I look at a stretched string here, if I hit it, then it bobs up and down here in the middle, and then the frequency will be determined by the speed of sound in the material divided by twice the separation between the ends. And again, it dies down. Okay, this bobbing up and down will die down because, again, of losses. And also will have a width. And then finally here, if I have an LC circuit, inductor and a capacitor, again, if I inject a pulse into it, I see that, again, I get an oscillation. If I look, let's say, at a voltage across the capacitor here, I have this oscillation that dies down. And the frequency is given by, in this case, by the square root of 1 over LC, L being the inductor, C is the value of the capacitance. And this decay is due to losses. Now, in an electrical circuit, where the losses come from? Well, they come from ohmic losses, essentially dissipation in the wires, according to Ohm's law. So that all these kinds of oscillators, whether they're pendulum or mass spring, a vibrating string, or electrical oscillator, they all have specific frequencies, all right, they oscillate at, but they all have losses. And to make them into an oscillator, you have to overcome these losses. And as we saw that in the case of the pendulum, you need somebody to push. Here, you may also need somebody to push. Over here, you have to keep vibrating these things to maintain oscillation. And of course, in the electrical one, we add an amplifier to overcome the losses. Now, to then summarize, then we need to make an oscillator. Then we need a resonator that will determine the frequency for us, and we need a means of overcoming the loss. So if we have that, then we can get this oscillation, this nice oscillation that comes out from that black box I showed you earlier. Now, what about the laser? Okay, how does the laser work? Well, in lasers, because lasers is an oscillator, we need a resonator, first of all. So let's look at how we can create electromagnetic resonator. Well, just like this is very similar to the stretched string. We need two ends, we need two nodes, and here we have, to create this, we have two mirrors. Here are two mirrors M, and they're spaced a certain distance L apart. Now, the lowest frequency that can fit between these two modes and oscillate backwards and forwards between these two modes is the one where half the wavelength, where L is half this wavelength, because the wave would be about this size. Now, such a wave would be able to bounce backwards and forwards between the two mirrors, and will be at that frequency, determined by, in this case, will be determined by F equals C over 2L, because lambda times the frequency equals the velocity of light. So either that the wavelength is 2L, all right, or its frequency is just C over 2L. Okay, so this is then the lowest frequency that will be supported in this kind of structure with two reflectors or two nodes at the ends, just like in the vibrating string. Now, this oscillation will die down. If I injected some light in here and I get it to oscillate like this, it will die down because of losses. And again, in the frequency domain, this will have a width. Question is, where are the losses in this case? Well, the losses come from the reflection in the mirrors. If the reflectivity of the mirror is not perfect, then every time the light bounces from one mirror to the other, then the amplitude will go down, and very quickly it will die down altogether. So in order to make this then oscillate, or essentially laze, we need to overcome these losses. But before I get to this, I want to talk about other modes in this kind of resonator. So far I've talked about this one where only half the wavelength fits between the two mirrors, but I can also get a condition where a full wavelength fits between the two mirrors. These are sort of normal modes of these resonators. Now, where lambda 1 was equal to 2L, and F1 was C over 2L, in this case, lambda 2 is essentially L, or I like to write it as 2L over 2, but I can cancel to the 2's, and I get L. And the frequency is just 2C over 2L. So here we had 1 times C over 2L, here is 2C over 2L, and so here I'm spacing it along in the frequency, along the frequency scale. Here's my F1, and here's F2, and the separation is C over 2L, and each one has a width because of the losses. Now we can go a little further here and consider a few more of these oscillations. In this case, I have 1.5 waves that will fit between the cavity, between the two mirrors, or within the cavity, and then the wavelength will be 2L over 3 instead of 2L over 2, and the frequency will be 3C over 2L instead of 2C over 2L here. So now, again, you can see I'm going to stack them up, F1, F2, and 3, and the separation is equal between them, which is C over 2L. And we can go to many more, and I'm jumping here to what we call the Qth mode, lambda sum Q, and just because the way I was doing it previously, you can see that the wavelength will be 2L divided by Q. This is the Q number, just like in here. This was 3, 2, 2, 1, and now in this case will be the Qth mode. And the frequency will be just Q C over 2L, just like here we had 3C over 2L, 2C over 2L, and so on. So on the frequency scale then, we have all these resonances that come from, that I can excite in one resonator, and can be as high as you want it. And the width, each one will have a width because of the losses. Now, not all the widths will be the same because not all the losses some losses will depend on the wavelength or the frequency you're at. So since the mirrors can have loss, but the loss can depend on the wavelength, and so these widths can vary. So now this explains the resonator, and just let me summarize the information here. We have a typical now a laser cavity which is again 2 mirrors spaced by L. In this case, I'm going to take L as 100 centimeters, or 1 meter. If I choose for the wavelength to be half a micron, or 5 times 10 to the minus 5 centimeters, then Q comes out to be, this Q, this integer we talked about, comes out to be 2L over lambda from this formula here, and is 200 divided by 5 times 10 to the minus 5, which comes out to be about 4 times 10 to the 6, which means that Q has the value of few million, all right, which means there are lots of little waves in here in a cavity of 100 centimeters separation. The frequency associated with that is, again, f sub q from here is 6 times, comes out to be 6 times 10 to the 14 hertz. And the width will depend on the losses, which are mainly due to, let's say, mirror losses and so on, which we'll get into later. So then to make an optical oscillator, or like a laser, we need the resonator that we have talked about, but it has not just one frequency, but has many frequencies, and we have to have a means of overcoming the loss, and that that comes about with a light amplifier. So the light amplifier is the key element in a laser. Because without the amplifier, you can have all these cavities, empty cavities that do absolutely nothing for you. But in order to create lasers out of them, then you have to put an amplifier. Okay, so here is then the laser. Here's the cavity that we talked about, and then we have to insert this amplifier. And this amplifier, which we will talk about later in more depth, this amplifier then provides gain for the light that goes backwards and forwards between these two mirrors to overcome the losses, wherever the losses come from. And the whole idea is to make the losses as small as possible, so you don't need to use a big amplifier, because in order to generate this gain, which we'll talk about later, it costs a lot of effort, a lot of money, and so on. So we want to minimize the gain that's needed. But we certainly have to have enough gain to overcome the losses. And here, for example, I have this amplifier, this gain of this amplifier located at this particular frequency. And over here, I have all the modes of the cavity that we talked about before. But if there is one of these cavity modes under the bandwidth of this amplifier, then if there is enough gain to overcome the loss, then I can get this to oscillate. And in fact, here it is. As we know, that this width of the cavity comes about because of the losses in the cavity. But if I have enough gain to overcome the losses, then I collapse this width to this delta function that we had before. And the output that comes out from this mirror, if I put some transmission in this mirror here, I leak a little bit of light out, then that light will have this spectrum, this very narrow spectral width, or in terms of the time domain, I have this lovely oscillation here that has a constant frequency determined by this cavity mode and a constant amplitude. So I think this will be a very fitting time to stop for this first session, because I brought you just to the stage where I think now you want to know where this gain comes from that makes lasers possible. So when we come back, we'll start exactly with that topic.